Okay, we just finished our discussion of the principal quantum number n, and now we want to move on to the angular momentum quantum number. So here's the consider. Consider the angular momentum quantum number. What is its symbol? What does it indicate about the orbital in which the electron is likely to be found? And what are its values? So we're looking for symbol, we're looking for its meaning, and we're looking for its values. So let us go back to our beautiful concept map. Yikes! Okay, well, somewhat beautiful concept map of quantum numbers, four quantum numbers. We've pretty well filled out everything we need to know about the principal quantum number. Now, let's go with black and the angular momentum quantum number. What is its symbol? Its symbol is L. As I said, usually it's a script L. It's hard to make that beautiful script L. So on the computer, I've used a large L most of the time. Now, what is its meaning? The meaning of the angular momentum quantum number is that it tells us the shape, it indicates the shape of the orbital. Yeah. Well, that must mean what? We're going to find out that based on based on L, we're going to have different shapes to the orbitals. And we'll get into those shapes more specifically a little later. Good, but that's the meaning. It represents the shape of the orbital. Now, fine, what are its values? Well, its values depend on, okay, first of all, the values depend on n. And what are those values? It's all integers between 0 and n minus 1. Okay? So all positive integers between 0 and n minus 1. It always begins with 0, and then we go from 0. So if n is equal to n equals 1, well then what? 1 minus n minus 1 is 0, and so the only value I would have is 0. If n equals 2, then what happens? I start at 0, and I'm going to go all the way up to n minus 1. So 2 minus 1 is 1, so my values would be 0 and 1. Okay? Hey, I think it's enough to answer a question. Let's go see. All right, what is the symbol? We know the symbol. The symbol is L. Good. What does this indicate about the orbital? This tells us about the orbital shape. It tells us the shape of the orbital, shape of that most likely location where an electron is to be found. And what are its values for n equals 2? Hey, we just did that. N is equal to, we know we start at 0, we go to n minus 1, and we use all positive integers here, all positive integers. And so we go from 0, n minus 1, n minus 1, so that's 2 minus 1 is equal to 1. So we have two quantum numbers. When n is equal to 2, we have two quantum numbers. Now, there is something you need to understand. We cannot think math here. 0 has meaning. This means something to us, as I'll show you shortly. This has meaning. It does not mean 0. It is really just a symbol for a specific L value, right? So don't say, oh, well, it's 0. There's no L value here. No, this is an L value, and the value of L in this case is 0. And in fact, we have two values, right? When n is equal to 2, we have two L's. L equals 0 and L equals 1. Okay, that's an L, even though it maybe look like an E. That's an L. Good. Next question. Here we go. Okay, consider the n equals 4 energy level. What are the possible values for L at this level? Is 4 a possible value for L at n equals 4? Okay, this is one for you to do. Pause me, and when you have the answer, bring me back to life. Okay, ooh, here I am coming back to life. Okay, the n equals 4 energy level. Okay, we said what? L is all values from 0 to n minus 1. N is 4 minus 1, so that means that is all values from 0 to 3, all positive integers. That means I have 0, 1, 2, and 3. So my L values for n equals 4, I have 4 of them. 1, 2, 3, 4. Hey, guess what? When my n is equal to 4, how many values of L did I have? 4. When my n was equal to 2, when my n was equal to 2, how many values of L did I have? 2. Hey, you know what? N also tells me the number of values of L I have. So when n is equal to 5, how many L values do I have? 5. And if these are each different shapes, that means I would have 5 different shaped orbitals. Good. So is 4 a possible value of L? Let's see. 0, 1, 0, 1, 2, 3. Is 4 a possible value? I don't see it. The answer is no. Okay, good. So L cannot be 4 when n is equal to 4. Got it? All right. Let's move on. Here we go. Aha, finally. Consider L equals 2. Okay, we know what to do there. What is the shape of this orbital? Of this orbital? There may be more than one orbital here. Well, no, I don't think so. Yeah, we'll see. I'm not sure. L equals 2, and we want to know the shape, right? What is the abbreviation for this shape? Okay, and how many of these do I have? Well, I think we need to learn a little bit more. So here we go. I said that L had to do with the shape of the orbital. And how is that the case? Well, let's write down some values of L. L, and then shape, and then abbreviation, and then the number of the shape at a given n, at a given level, right? Good. So what did we say? L always starts with what value? L always starts with what value? Let's see. L always starts with what value? L always starts with 0. Okay, so we start at 0. So let us go and back to our question. L always starts at 0. So L is 0, L is 1, L is 2, L is 3, L is 4. Good. What's the shape? Well, the shape of L equals 0 is what we call a sphere. Good. And believe it or not, the abbreviation for sphere is S. And we have only one of those at every energy level. Got it? And what's a sphere? Well, this is a sphere. And we want to thank our fine folks at Peterson Prentice Hall here. This is the 1s sphere. This is the 2s sphere. This is the 3s sphere, right? 1 stands for what? That's my n. And so this is what we'd call the 1s subshell here, 1s, 2s. That means I'm at the n equals 2. And what's my orbital look like? For L equals 0, it looks like a sphere. Got it? That's pretty simple. Next, when L is equal to 0, what do I get? I have something that is technically called a dumbbell. I tend to like to think of it as a peanut. I'll accept either answer on my quiz and test. Now, why do I like peanut? Because the abbreviation is a P, and a dumbbell and a peanut look kind of alike. Now, how many of these do I have at a given n? 3. Okay, good. So let's take a look. What do we mean by a dumbbell? Okay, here are my p orbitals. This is what p orbitals look like. In reality, they look something like that, kind of blobs, right? And remember, that's high density, meaning that's the most likely spot for an electron. Out here, it's less likely. It's still 90% of the time I'm going to find my electron in one of these two places. Okay, but the darker the color, the more dense the probability of finding that electron. Okay, so we have this is really just showing you what what a real orbital would look like. Now, here are my three types. I can have a PZ, meaning I have a P in the vertical direction. I can have a PX, which is a P in the X direction, and I can have a PY, which is a P in the Y direction, right? And you can see why they're called dumbbells, but they almost look like peanuts, don't they? Good. So those are my 3p orbitals that I would have. So I have 3p orbitals at every n, right? No, I shouldn't say at every n. That's the most I can have. I have to be careful. I don't have p's when n is equal to 1, remember? When n is equal to 1, I only have one shape. And we always start, I guess that's another important point. We always start with my L equals 0. So when I have n equals 1, I only have this. When I have n equals 2, I have this and this. So when I have n equals 3, what am I going to have? When n equals 3, there's going to be three shapes. What are they? There's going to be a L equals 0, an L equals 1, and an L equals 2. That means I'm going to have a sphere. I'm going to have a peanut, and I'm going to have something that we can call a double dumbbell, or what do you think? A double peanut. Oops. Double peanut. And we're going to have that as its abbreviation is D, and there are going to be 5 of those. And what do we mean by double peanut? There we go. It's kind of like a peanut in this direction and a peanut in that direction, or a peanut in that direction and a peanut in that direction, or a dumbbell in that direction and a dumbbell in that direction, and so forth until we get to the Homer Simpson, right? Which is really what? Peanut. Donut. How can you go wrong when you have a peanut and a donut together? Wow, you have protein, fat, and sugar. Nothing beats that. No, it's not really called the Homer, but it's kind of nice to think of that, isn't it? Yum, donut. Good. So these are my 5 d orbitals. Great. And when can I have 5 d orbitals? Well, I must have, let's try to clean this up a little bit. When I have n equals 3, that means I have 3 L's. I have an L equals 0, an L equals 1, and an L equals 2. And this would be my sphere, this would be my peanut, and this would be my double peanut. So I must have at least an n equals 3 for me to have a D. Now, having said that, how many S's do I have at n equals 3? Well, I have how many? 1. How many P's do I have at n equals 3? Well, I have 3. How many D's do I have? I have 5. Hey, you know what? I'm starting to see a pattern, aren't you? 1, 3, 5. 1, 3, 5. What do you think's next? Well, I can guess, can't you? 1, 3, 5, 25. No, 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 no. 1, 3, 5, what? 7. That's correct. We're going to have 7 of the next one, and these are called multi-globed. Multi-globed, is that right? Multi-globed. That confused. Multi-lobed. Sorry. Multi-lobed. And how that's for n L equals 3. So when L is equal to 3, I have multi-lobed, and we call that an F orbital. And I have no idea what multi-lobed looks like. It's too hard for me to think about, and it's probably like the Geary Band show up in Chicago, which says all kinds of weird shapes to it. And we don't have to worry about what a multi-lobed looks like. Now, having said that, SPDF, we really don't know the shape for L equals 4, but it becomes G. And how many do we have? 9. And then when L equals 5, I don't talk about the shape. FG, and what do you think the abbreviation is? H, and how many are we going to have? 11, and it goes on and on. And that's how we can figure out our shapes of quantum for our L quantum number. So let's answer our question. L is equal to 2. What is the shape of this orbital? Okay, so L is equal to 2. So L equals 0 was a sphere. L equals 1 was a peanut. L equals 2 is a double peanut. Is that right? Let's go back and look. Okay, L equals 0, sphere. L equals 1, peanut. L equals 2, double peanut. How many of those are we going to have? We're going to have 5 of those. So let's go up here. What is the abbreviation for this? It's a d orbital. And how many do I have? I will have 5 d orbitals at L equals 2. Okay? Good. All right, let's see if you can do this. There you go. L is equal to 1. What is the shape of this orbital? What is the abbreviation for this shape? How many of these orbitals can exist for L equals 1? All right, pause me and answer the question. All right, what did you get? Well, I always like to start with L equals 1, L equals 0, L equals 1. When L is equal to 0, it's always a sphere. When L equals 1, that means it is a P. How many spheres would I have when L is equal to 0, 1? How many P's? 3. So let's answer our question. What is the shape of this orbital? Okay, if L is equal to 1, what do I have? I have a peanut shape. Good. What is the abbreviation for this? Well, it is a P. And how many of this orbital do I have? I would have 3 P's for L equals 1. Good. Excellent. Hey, did we answer this question up here? Really? I guess we didn't. What's the shape? It is a double peanut or double dumbbell. Sorry, folks. Good. Any more things here? No. Let's go to the next question. Consider the 5p subshell. How many orbitals can exist at this subshell? Okay, 5p. Okay, that means what? That means I'm at n equals 5, and my L is a p. So when my L is p, let's see. Okay, hold on. Let me write down L. 0, 1, 2, 3. My abbreviations are S, P, D, F. The number is 1, 3, 5, 7. Okay, so when I have a P, that means my L is equal to what? P, L is equal to 1. So I have L equals 1. So this means I have N equals 5, L equals 1. How many orbitals can exist at this subshell? Okay, we have it right here, right? At the N at n equals 5, L equals 1, or at the 5p subshell, I would have 3p orbitals. All right? What is the maximum number of electrons which are likely to be found at this subshell? Hey, remember Pauli exclusion? Pauli said what? Maximum of 2 electrons per orbital, right? So how many orbitals do I have? I have 3 orbitals. 3 times 2, so I have 3 orbitals times 2 electrons per orbital. So how many electrons are likely to be found? 6 electrons are likely to be found where? At the 5p subshell. Great. What is the maximum number of electrons which are likely to be found in one 5p orbital? One 5p orbital. This question is saying how many can be found in all the 5p orbitals together, right? And how many orbitals did we say here? There were 3 orbitals, but now we're looking at 1 orbital. According to Pauli, how many electrons can be found in 1 orbital? Only 2 electrons. So does this matter if I say how many electrons can be found in 1 5p or 1 2000 F or in 1 100s? It really doesn't matter if we're talking about 1 orbital, regardless of where it is. How many electrons can be found at maximum in 1 orbital? 2. And that's it. Got it? And you have to be careful when you read these. read these questions carefully. Are they talking about one orbital, or are they talking about a whole collection of orbitals? In this case, are they talking about the collection in this subshell? Excellent. Here you go. Give this a shot. Consider the 4s subshell. How many orbitals can exist at this subshell? What is the maximum number of electrons which are likely to be found at this subshell? What is the maximum number of electrons which are likely to be found in one 4s orbital? Okay, pause it and bring me back when you're ready. Okay, how many orbitals can exist at the 4s? Okay, well, let's go back and look at my beautiful picture. When I have an s, here's the s, how many do I have? I have one. So that means at the 4s, I only have one orbital. I have one orbital. By the way, what's the shape of this 4s? We would say it is what? It is a sphere. Sphere. Good. What is the maximum number of electrons which are likely to be found in this subshell? Well, I have one orbital. And how many electrons max per orbital? 2 electrons per orb. So what's the maximum number of electrons here? 2 electrons. What is the maximum number of electrons which are likely to be found in one 4s? Well, there's only one 4s, so my answer is 2. Hey, that was easy. All right. Well, that's our discussion of the second quantum number. Let's finish here, and when you come back, we will finish with our magnetic quantum number and our spin quantum number. All right, bye.